this video, we are going to find positive integers x and y such that xy all to the power y equals y to the power x. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. My first step would be to rewrite the equation as x to the power y equals y to the power x over y to the power y. So the index becomes x minus y. Now, the left-hand side is a positive integer because it's a positive integer to the power of another positive integer. So that means the right-hand side also has to be a positive integer. Then from this, we can tell that the exponent at the right, x minus y, cannot be negative, because if it's negative, then the whole thing will become a fraction with 1 as the numerator, so which is less than 1. So that's impossible, and that means we will have x is at larger than or equal to y, or I would say x is at least y. Then we can divide this equation into two cases. The first case is when x equal to y, and of course the second case would be x is larger than y. So for the first case, if x is equal to y, then the exponent at the right is 0. Then x to the power x equals y to the power 0, and that's 1. And from this, the only solution would be x equals 1. And of course, at the same time, y also has to be equal to 1. Then we quickly finished the first case. As for the second case, for x is larger than y, I'm going to further divide both sides by y to the power y. So then, x over y all to the power y equals y to the power x minus 2y. The reason that I do this is that we have assumed that x is the larger number. So then, after doing this division, for the left side, x over y is a number that is still larger than 1. This number inside the bracket is still larger than 1. And when this number is brought to this y power, as y is a positive integer, the left side as a whole must also be larger than 1. Now from this, we know that the right side, y to the power x minus 2y, a positive integer to the power of another integer, is again larger than 1. So from this, we can say that this is also a positive number. So that means x minus 2y is larger than 0. In other words, x is larger than 2y. So it didn't only show that x is larger than y, it's even larger than 2y. And so we know that the right side is actually y to the power of a positive integer. And so, in particular, it's an integer. So that means x over y also has to be an integer. And so, apart from the fact that x is larger than 2y, we know that y has to divide x. Now at this point, to make the equation look easier, to avoid using fractions, I'm going to let x equals ky, some constant multiplied by y. And this constant is an integer. Then our equation becomes x over y equals k to the power y equals y to the power ky minus 2y, and then k to the power y equals y to the power y times k minus 2, taking out the common factor at the exponent, and so we have k equals y to the power k minus 2. Now we have something interesting, is that on the left we have a positive integer k, but for this integer k is at the exponent of the right hand side. So then as k goes up, increases, then the left side will grow really slowly, but for the right, it just may grow very, very fast. So then there will be very few solutions occurring when k takes a small value. So to write this out rigorously, not just saying out the idea, we have to establish some bounds on the variables that we are dealing with at the moment, which are k and y. So firstly, for y, actually it cannot be 1, because if it's really 1, then k will be equal to 1 to the power k minus 2, and it also has to be 1. And from this, x is equal to 1, so we have already achieved this, which is in the first case when x is equal to y. So we'll just have to disregard this part at the moment. And for y larger than 2, we can say that k is larger than or equal to 2 to the power k minus 2. There are two ways to reduce the number of solutions at this inequality. The first one is by induction. For this, I'm going to claim that this inequality won't hold when k is at least 5. Maybe I should move this so-called the word method to the next line to avoid confusion. So the base case is when k is 5, two to the power k minus 2 equals 8 and is larger than 5. So it's a tick. Assume that say m is less than 2 to the power m minus 2 for some m larger than 5, then 2 to the power m plus 1 minus 2, I can write that as 2 to the power m minus 1, and that is just double of 2 to the power m minus 2, so it's larger than 2m, and of course this is larger than m plus 1. So I can quickly say that by induction, the claim is true. That's the first method to show this. And my second way to show this is actually to use some calculus. Is that starting from k equals to 5, where we know that the base case holds, and then the growth rate of the function at the right, 2 to the power k minus 2, is equal to same function multiplied by natural log of 2, and that is larger than k times log 2 when k is at least 5. of course, is larger than 1, which is the growth rate of the function at the left, which is just k. So again, we have proved this claim. Now, from these proofs, we know that our inequality can only hold when k is at most 4. So then we can test them one by one. When k equals 4, then 4 equals y to the power of 4 minus 2. So y squared equals 4, and that means y equals 2. And at the same time, x is just 4 times 2, which is 8. When k equals 3, we have 3 equals y to the power of 3 minus 2. That means y equals 3, and x equals 9. And finally, we can test also when k equals 2. 2 equals y to the power 0. And we have no solution for this case. So summing up, we have xy to be either 1, 1, or 8, 2, or 9, 3. Of course, we can also check, which is that for the case 1, 1 is obvious. For the case 8, 2, xy to the power y would be on one hand 16 squared, and on the other hand 2 to the power 8. So they are both 256. Whereas for the case 9, 3, the left side equals to 27 cubed, while for the right side is 3 to the power 9, and they're actually the same number. So these three are valid solutions, and this is our final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.